Do you ever notice how, like, in sci-fi movies, they're always warping space-time, like ripping holes in reality?
Oh, yeah.
Well, today we're going deep on whether that's actually possible at all.
Right.
We're looking at an article. It's called Can Space-Time Self-Repair?
Okay.
And the science here is way more interesting than fiction, let me tell you.
It really is fascinating stuff.
Yeah.
There's some pretty big concepts we're going to try to unpack.
Yeah.
You know, from like Einstein's theory of gravity to the just mind-boggling world of quantum mechanics.
Yeah.
All to explore just how resilient space-time actually is.
You know, you've probably heard that analogy. Like a bowling ball on a trampoline to describe gravity.
Right.
That's Einstein's general relativity in action.
Yeah.
But how does this, like, fabric of space-time react to truly extreme forces?
Yeah.
Like, could it actually rip?
That's where things get interesting.
Yeah.
It's important to remember that space-time isn't a material like a sheet that you could just like tear.
Yep.
It's more like a dynamic framework, I guess.
Okay.
That kind of defines the relationships between events and objects.
Okay.
And according to Einstein's theories,
Right.
the geometry of space-time is constantly being influenced by the matter and energy within it.
So it's constantly changing and adapting.
Exactly.
Wow.
And while it can certainly deform under extreme conditions, think black holes, the idea of it ripping like a piece of fabric is a bit of a misconception.
Okay. So black holes, these are always a popular topic.
Yeah.
They seem to be a pretty good test of space-time's limits.
Yeah, for sure.
I mean, there's that singularity at the center.
Right.
Where gravity becomes infinitely strong. Does that mean space-time is breaking down there?
The singularity is definitely a point where our current understanding of physics starts to break down.
Right.
General relativity, which works incredibly well on large scales, predicts infinite density at the singularity. But many physicists believe that quantum mechanics, which governs the subatomic world, must come into play at those scales and prevent a true rip from happening.
So it's like these two fundamental theories of the universe.
Yeah.
General relativity and quantum mechanics are sort of battling it out at the heart of a black hole.
In a way, yes.
Wow.
And that's why physicists are so eager to develop a unified theory of quantum gravity that can like reconcile these two frameworks.
So until we figure out quantum gravity, we're left with this mystery of what's really happening at the singularity.
Exactly.
But what about other extreme phenomena like wormholes?
Yeah.
Aren't those often depicted as sort of tunnels or shortcuts through space-time?
Right.
Could those be created by cutting through the fabric of space-time?
Wormholes are definitely fascinating theoretical objects.
Yeah.
But even if they exist, they wouldn't be created by cutting through space-time.
Right.
The current thinking is that they would involve warping or distorting space-time in incredibly complex ways, but not actually severing it.
Okay, so space-time is starting to sound a lot less fragile than sci-fi might lead us to believe.
Yeah.
But are there AOI theoretical scenarios where it could be damaged or disrupted?
There are some truly mind-boggling possibilities out there.
Okay.
One example is the concept of cosmic strings.
Okay.
These are hypothetical, one-dimensional objects that could stretch across vast distances of the universe.
Okay.
Imagine them like incredibly thin, incredibly dense wrinkles in the fabric of space-time.
Okay, so if space-time is like a smooth sheet, these cosmic strings are like creases or folds in the sheet.
That's a good way to visualize it.
Okay.
Now, what's really interesting is that if two cosmic strings were to intersect, the energy released at that point could potentially be enormous.
Wow.
We're talking potentially enough to disrupt space-time in ways we can't even fully comprehend.
So even if space-time can't really rip in the traditional sense, there could be these localized points of extreme disruption.
Exactly. But remember, cosmic strings are still hypothetical.
Right.
We haven't observed them directly. So this is all very much in the realm of theoretical physics.
Okay, so it sounds like even the most extreme theoretical scenarios involve distorting or disrupting space-time, but not necessarily destroying it completely. Is that because there's something fundamentally preventing it from being destroyed?
That's a question that leads us to the incredibly strange world of quantum mechanics.
Okay.
Specifically, we need to talk about something called quantum foam.
Quantum foam.
Yeah.
It sounds harmless,
right,
but at those scales, even the seemingly stable fabric of space-time gets incredibly dynamic.
Absolutely.
Yeah.
Quantum foam is the idea that at the Planck scale, That's about 10 to the power of minus 35 meters.
Wow.
The smallest scale imaginable.
Yeah.
Space-time is not smooth and continuous like we experience it.
Right.
Instead, it's a chaotic sea of fluctuations.
Right. Wow.
With tiny regions constantly popping in and out of existence.
So it's almost like space-time is constantly bubbling and fizzing at this subatomic level.
That's a great analogy.
Wow.
And some physicists believe these quantum fluctuations might actually play a crucial role in space-time's ability to self-repair.
Here's where it gets really interesting.
Right.
So how would these tiny quantum fluctuations prevent large-scale damage to space-time?
It comes down to the idea that quantum fields,
okay,
which are the foundation of all matter and energy,
yeah,
inherently seek stability.
Okay.
So even if there's a major disruption like the collision of two black holes,
Yeah.
these quantum fluctuations might act like a sort of buffer,
Okay.
smoothing out the disruption before it can cascade into a catastrophic tear.
So it's almost like the universe has this built-in microscopic maintenance crew.
Yeah.
Constantly patching things up at the quantum level.
That's a great way to think about it.
Wow.
And it leads to some profound questions about the nature of space-time itself. Is it fundamentally unbreakable or just incredibly good at adapting and repairing itself?
Right.
To explore that further,
Yeah.
we need to delve into some even wilder theories.
All right.
But we'll save that for part 2 of our deep dive.
Okay. Sounds good.
So, welcome back to our deep dive into space-time's ability to self-repair.
Okay.
We've established that space-time is surprisingly resilient.
Right.
But can we see this cosmic healing in action?
That's a great question.
Yeah.
Are there specific instances,
Yeah.
like real-world events, that show this happening?
There are. And perhaps the most dramatic examples come from the collisions of black holes and neutron stars.
Wow.
These events are so cataclysmic.
Yeah.
They literally shake the fabric of space-time,
Yeah.
generating ripples that we could detect here on Earth.
You're talking about gravitational waves, right?
Like flash.
We touched on those earlier.
Yeah.
So if space-time were fragile, these waves would look pretty messy, wouldn't they?
Precisely.
Yeah.
Imagine a perfectly calm pond. Now toss in a huge rock.
Yeah.
You'd expect chaotic waves, right?
Right.
But that's not what we see with gravitational waves from these collisions.
What do we see then?
What's remarkable is that even after these incredibly violent mergers, the gravitational waves we detect are smooth and unbroken.
Wow.
It's like space-time absorbs the impact and settles back into a new equilibrium without any lasting scars.
So even when faced with forces that could theoretically rip apart the fabric of reality, space-time seems to just shrug it off.
It really does.
That's pretty impressive.
Yeah.
But it makes you wonder,
Yeah.
is there anything out there that could truly push it to the breaking point?
Well, as we discussed earlier, cosmic strings are one theoretical possibility.
Right.
If two of these incredibly dense, one-dimensional objects were to intersect, the resulting energy release could be mind-boggling.
Okay, so maybe cosmic strings are the rocks big enough to make that pond go haywire.
Yeah, that's a good way to put it.
Yeah. But we haven't actually observed cosmic strings, right?
Not yet.
Okay.
They remain hypothetical for now.
Yeah.
But their potential impact on space-time underscores just how much we still don't know about the universe's fundamental workings. There could be other phenomena out there beyond our current understanding that could truly challenge space-time's integrity.
So there's always the possibility of some unknown cosmic curveball.
Absolutely.
Wow.
That's what makes physics so exciting.
Right?
We're constantly pushing the boundaries of our knowledge.
Yeah.
Exploring the unknown and trying to piece together the puzzle of how reality works.
It's both thrilling and a little bit terrifying at the same time.
Yeah, I know what you mean.
But I'm curious, are there any clues about the mechanism behind this self-repair?
Yeah.
We've talked about the what space-time seems resilient.
Yeah.
What about the how?
To really understand the how, we need to dive into the theoretical frameworks that try to explain space-time's behavior. And that means venturing into the realm where general relativity and quantum mechanics meet, or rather, where they clash.
We've seen some pretty compelling evidence so far that space-time is surprisingly tough.
Yeah, it's pretty remarkable.
But the how behind this self-repair is what really gets me. It's like the universe has this hidden healing power, and I want to know its secret.
Yeah, well, that's a question that takes us right to the cutting edge of theoretical physics, as we've hinted at before.
Yeah.
It's all about the interplay, or maybe we should say clash, between general relativity and quantum mechanics.
Right. Those two giants of physics,
Right.
They seem to describe the universe perfectly.
They do.
Until they don't.
Right.
Like when we're talking about the extreme conditions of a black hole singularity.
Exactly. And that's where the search for a theory of quantum gravity comes in.
Right.
It's like the holy grail of modern physics.
Yeah.
A framework that could finally unify these two pillars of our understanding.
So quantum gravity is like the ultimate cosmic translator.
Yeah.
Helping us understand how gravity works at the quantum level.
That's the idea.
But how does that connect to space-time's self-repair?
Well, one of the leading contenders for quantum gravity is string theory.
Okay.
And it proposes something truly radical.
Okay.
That the fundamental building blocks of the universe aren't point-like particles,
right,
but tiny vibrating strings.
Now, these strings aren't like the ones on a guitar, right?
You don't know.
But the idea of their vibrations helps us understand how they might give rise to space-time itself.
Precisely. String theory suggests that space-time as we experience it emerges from the intricate interplay of these vibrating strings.
Okay.
Imagine like a tapestry.
Okay.
Woven from countless threads.
Yeah.
Constantly shifting and interacting.
Yeah.
That's kind of a glimpse into the string theory picture of space-time.
So space-time isn't this fundamental entity.
Right.
But rather it's a kind of emergent property.
In a way, yes.
It's almost like a hologram. Like even if you damage a small part, the overall image remains intact.
That's a very insightful connection.
Thanks.
And it hints at how space-time's self-repair might actually work.
Okay.
If space-time is constantly being woven and rewoven by the interactions of these strings,
right,
then disruptions, even extreme ones, could be absorbed and integrated into the overall structure.
So even if a few threads are broken or disrupted, the overall tapestry of space-time remains?
Yeah.
It's kind of like how a spider web can flex and rebound without falling apart.
That's a great analogy.
Yeah.
And it highlights a crucial point.
Okay.
Space-time's resilience might not be due to some special force field.
Right.
But it could be a natural consequence of its underlying dynamic structure.
That makes me think of those incredible slime molds.
Oh, yeah.
They can be cut into pieces and still reassemble themselves.
Right.
It's like they're less an individual organism and more like a self-organizing collective.
That's a fascinating parallel. And some physicists have even proposed that the universe itself might exhibit similar properties. A kind of self-organizing system that naturally tends towards stability and complexity.
So space-time self-repair could be a reflection of this deeper cosmic principle.
Potentially, yeah.
Like it's not just a random occurrence, but part of the fundamental fabric of reality.
That's a profound thought. And it opens up a whole new way of looking at the universe.
Yeah.
Perhaps the laws of physics themselves are, in a sense, designed to ensure the universe's continued existence.
It really makes you think about our place in the cosmos.
Yeah.
It's like we're not just passive observers of the universe.
Right.
We're part of this grand interconnected system that's constantly striving for balance and survival.
It's a humbling realization, and it underscores how much we still have to learn about the true nature of reality.
So after this incredible deep dive,
Yeah.
where do we land on the big question? Can space-time self-repair?
I think it's safe to say that all the evidence from the smooth gravitational waves we observe to the mind-bending possibilities of string theory points towards a resounding yes.
Space-time might not be invincible, but it's certainly more resilient than we might have imagined.
Yeah.
It bends, it flexes, it adapts, and ultimately it endures.
And perhaps that's the most important takeaway.
Yeah.
That the universe, at its most fundamental level, seems to have this incredible capacity for self-preservation.
It's a thought that leaves me feeling both awestruck and strangely comforted.
How do we get that?
The universe may be full of mysteries and challenges, but it also seems to have this built-in drive to keep going, to keep evolving.
Yeah.
And that, to me, is a truly beautiful idea.
Indeed. And it's an idea that should inspire us to keep exploring.
Yeah.
To keep asking questions and to keep pushing the boundaries of our understanding. Because the more we learn about the universe, the more we realize just how much more there is to discover.
Thank you for joining us on this incredible journey into the self-healing nature of space-time.
Yeah, thanks for having me.
It's been a deep dive into the mysteries of the cosmos, and we hope it's left you with a sense of wonder and a thirst for more knowledge.
I hope so.
Until next time, keep looking up and keep asking questions.